Welcome. The title of today's notes worksheet is Relations and Functions. And today's lesson actually represents a slight shift in our curriculum. We're going to move away a little bit from the algebraic skills and move more into the algebraic modeling between two variable quantities. So we'll just kind of set up the foundation today and then kind of go from there, do a lot of exploration in different families of relationships and functions and so forth. So let's start it out here. Just we'll do a little compare and contrast as we go through the first part of this lesson. So on your paper you have a relation and then really kind of the definition of a function right here. So let's start it out with just a relation. And so I have any set of ordered pairs essentially. So what that basically means is it's a relationship of any two variable quantities. So let's put that in place if we can. And then, as I said, play a little compare and contrast with that and a function, of course. So let me just make sure I get this in here for you. So relationship between any two variable quantities. All right, very nice. Now a function is a very particular type of relation. And we're going to look at it both conceptually and mathematically here. So let's start it out with conceptually and then sort of go from there. So it is a relationship between two variable quantities. We'll kind of start that piece out here. So a function is a relation. But well, let's see. Let me put this in place and then we'll kind of talk about it. So it is a relationship, as mentioned. And then here's the conceptual piece, where one variable quantity, and you've seen this before. So one variable quantity, and then here's the key phrase, depends on, and I'm going to underline that piece up here. So one variable quantity depends on a second variable quantity. Perfect. So functions express this notion of dependence. One quantity depends on a second quantity. So that's going to be the key for us just in terms of talking about just any two variable quantities or really one where it is either dependent on it or it is a function of it. And those two phrases go hand in hand. Now mathematically, this is probably something you've seen way back in Algebra 1 to kind of just look at a set of mathematical data and decide, hey, does this represent a function or does it not represent a function? If you remember correctly, there would be no repeat of the x values. That's as basic as we can get when talking about the definition of a function mathematically, that the x's can't repeat. What that really means to me, and this kind of is what we'll explore today with today's lesson, is that each x value can produce only one y value. So jot that in there if you don't mind. Only one y value. And again, we'll see what that means and we'll provide some context for it over the course of today's lesson. But again, just kind of going back from just a general understanding of functions, one quantity is a function of another quantity. What that means is one quantity depends on another quantity. Okay, well let's just kind of start it out here. I have an investigation, I believe, just below, and got to get us thinking about exactly that piece, and then we'll do some of the mathematics behind it. So here's what I have. A and B on your paper is basically I have two relations. So each set of ordered pairs represents a relation, and just what I'm asking for is, does it make sense for it to be a function conceptually, and is it a function mathematically? And these are very contrived, but they're just to get us to think about, sort of the differences between these two things. So let's start it out here. Letter A, it says 10 students SAT scores, math and verbal. Okay, so that's what I have, a relationship of two variable quantities right here. You've got the math score coming first and the verbal score coming second. Now, I guess, the question I would ask, just from a conceptual standpoint, is does the verbal score depend on the math score? And I'm hoping you would agree with me that the answer is definitely no. So does the verbal score depend on the math score? No. Is the verbal score a function of the math score? Then no. this relationship does not express the notion of dependence. And so as a result, we wouldn't consider one variable quantity to be a function of another variable quantity. And so the answer would be no right here. Now from a mathematical standpoint, if we were to look at this set of data, we would also kind of look at it in that each x does not just produce one y. And I'm wondering if you can kind of find where that goes astray here. And I'm seeing it in terms of these two ordered pairs right here. The way a function is defined, the 580 can't produce both a 500 and a 540. Unfortunately, that is just not how a function works. Each x can only produce one y. And so here, that's what makes it just mathematically not a function, if we were to just take a look at that set of data. And again, I contrived it obviously so this would work out, but I'm hoping you can kind of see that piece. All right, good. So a repeat on the x's there makes this not a function mathematically. Okay, very good. So that one was no. It is a relation, but it is not a function. Now letter B. National ACT scores from 2002 to 2008. And so I have a relation between the year and the national score. And so in 2002, the national score was 20.8. In 2003, the national score was 20.8, et cetera, et cetera. Each year produced a national score. So does the ACT score depend on the year the tests were taken? Absolutely yes. So if you kind of look at each of these, this score right here is dependent on the fact that those tests were taken in 2002. This score right here, even though it's the same score, everyone, but this score right here is dependent on the fact that those tests were taken in 2003. This score dependent on those tests being taken in 2004, et cetera, et cetera. Each of those scores is dependent on the fact that they were taken in that particular year. And so the answer is yes. And if the ACT score depends on the year, then it is a function of it. And there's our yes right there. And you can kind of see, again, each x produces only y. In 2002, it produced this national score. In 2003, it produced this national score. In 2004, it produced this national score. Each year produces a national score. And that's it. Each x produces one y. Wonderful. I'm hoping that just, again, solidifies just the ideas behind it. I kind of like that piece. It's just a little compare and contrast, if nothing else. All right, very good. So let's move on to kind of the next description, my next board here. And, you know, I guess I put this little sentence here in bold, and I would argue it's probably the most important sentence of the entire semester. If we can really understand this piece, then it allows us to do a lot of things with functions that might not happen if we don't really truly understand what's going on here. So let me read it, and then we'll kind of draw it out and just do some examples to back it up. So a function is a set of rules that tells us what to do to the input. So we start with an input, everybody, our independent variable, our x value, so to speak. We start with an input, and that input goes into a function. The function manipulates it. It's a set of rules that tells us what to do with it, and then out comes an output. And so what we're going to do is illustrate exactly that piece. There's a little flow chart right below there, and if you don't mind, let's kind of start this out with just our generic input. Our generic independent variable is going to be x, so just start with that if you would. Now you've probably seen these little function machines before, and I'll try to do this justice here, but basically it kind of looks something like this. There we go. It's a terrible one, but whatever. I can get it to go. And we'll just call this our function, and I'm going to call it function f. So basically what happens is this input goes into this function machine right here. And this function, again, is nothing more than a set of rules that tells us what to do to this input right in here. So this goes in. The function tells us what to do to it. It manipulates it in some way, and then it spits out an output. And that output, as we all know, is f of x. And that's it. Input produces output. And you can kind of see why that verbal definition up above falls in line with this right on here. Each x produces one y. This goes in, the function tells us what to do with it, and out comes one particular value. I can't get two particular values out of this. Okay, so an x produces a y. Okay, very good. So just in terms of our pieces here, this is going to seem a little elementary, I think, initially, but I think it pays off in the long run. What we're going to do with example 1 is just describe the function rules. If I was to give you any type of input, what would you do with that input in order to produce the output? So here is the mathematical description of our function, and so I guess I would like to verbalize it, that's all. So example 1 just says describe the function rules. And so if I was to give you an input here, what would you do to that input to get the output? What are the set of rules that would produce the output? Okay, well if I gave you 2, what would you do to the 2 to get the output? If I gave you 10, what would you do to the 10 to get the output? Etc., etc. I'm hoping you would all agree that in terms of our mathematical order of operations, we would multiply that input by 2. And keep this simple. Again, I think creating this mindset, though, does help us sort of in the long run. So anyway, here's what I would do. I would multiply the input by 2, and then I would add 1, and that's it. Whatever the input is. The input, as I said, can be 15, and I would multiply it by 2 and then add 1. The input could be A. I would multiply A by 2 and then add 1. The input could be a question mark. I would multiply it by 2 and then I add 1. Whatever the input is, the function just tells us what to do to it in order to get the output. Okay, cool. Let's do letter B. So same deal here. What would you do? What does this tell you to do just verbally? And just from my perspective, whatever my input is, it looks like the first order of business is to square the input. So square that first. And then after I square the input, it looks like I would subtract the input. So whatever it may be, whatever goes into that function, those are the two things that I would do in order to get the output. Okay, good. So I'm hoping everyone can translate this into something like this over here. All right. Now let's take a look at a particular type of function and then sort of look at the notation that goes behind it. And if we can understand sort of this piece specifically, is does our notation represent an input change or an output change, and then what to do with it in order to get it to be either evaluated or simplified. Again, I think it allows us to do a lot of things in this unit that might not be able to happen if we didn't understand this. So anyway, let's kind of go for it. As I look at this, f of -3, does this -3 here, does that represent an input to you, or does it represent an output to you? And based on probably your previous math courses, you would probably say that that is the input. Based on the notation there, that is the input. And so what that basically means is that's going to go into the function. And by the way, we should kind of verbalize what the function is telling us to do. This is what is called a quadratic function. We'll do some work, of course, with quadratics this semester. And I'm hoping you would agree that this basically says, in terms of what to do to the input to get to the output, I would square the input, then subtract the input, and then add 3. Okay, so basically I'm going to do that. -3 is my input, so I'm going to go ahead and square the inputs, subtract the inputs, and then add 3. So once I know it's an input change, that's pretty much exactly what I do with it. And let's see what we end up getting here, by the way. I get -3 squared, which is 9, minus -3, which is 12, and 12 plus 3 looks to be 15. So I'm seeing that piece right there, and that's it. That's pretty much what I'm going to do. Okay, so no matter what the inputs are, if I know what the function rule tells us to do with it, I should be able to pull it off. Okay, well let's go ahead and do letter B then. So same deal. I've got f of 2x, and so you can kind of see I had f of x defined as this right here. Now I have f of 2x. Does this 2x, everybody, represent an input or an output? Am I changing x or am I changing f of x? And in this case, it looks like I'm changing x. It was this, and as you can see, now it's this right here. And so as a result, everybody, that seems to be an input, that 2x. All right. And how do I treat inputs, of course? Well, very simply, I just follow the function rules on it. So if 2x is my input, I'm going to square my inputs. I'm going to subtract my inputs, and then I'm going to add 3. And again, this is just a skill. It's, as you can see, it's the beginning of a unit, so it's meant to just be an introduction. But it is a skill that we're going to want to perfect going forward. We're going to have a context for doing a lot of this type of manipulation over this unit, and it needs to be fairly automatic. So square the input, subtract the input, add 3. And then, guys, you're just going to have to play cleanup here. Don't forget your properties that we've been developing in the algebraic skills unit. So in this case, I would do 2x and square it, remove those parentheses, and I'm hoping you would see that would be a 4x squared. Minus 2x, not a big deal right there. And then how about plus 3? And there you have it. Nicely done. So f of 2x looks like this right here. Okay, good. Let's go get the next set, if we can here, and start developing your input change versus output change. So let's look at letter C. So in this case, notice it's 2 times f of x. And so the question is this an input change or an output change? Am I changing x or am I changing f of x? And in this case, it looks like x is the same, right? Right in there. It was x before, it's x right now. So notice it's not an input change. What I am doing is taking f of x, I'm taking the output or the function and multiplying it by 2. So notice the difference in the notation, especially between B and C. There was f of 2x, which I called an input change, and there's 2f of x, which now I'm calling an output change. Notice the difference there, please. Now, how would you deal with this? And by the way, I should probably just above put that function just so we have that. I know it's on the front side of your page. I think I saw it was x squared and then minus x plus 3. So that should give us a bearing to do C through G here. And I guess what I'm seeing, of course, is that if this is f of x, this whole thing right here, I'm going to essentially multiply it by a factor of 2. So this says take your f of x, and this is what f of x is, of course, and just multiply it by 2. So that's exactly what I'm going to do. Those entire set of rules, squaring the input, subtracting the input, and adding 3, that entire set of rules, that entire function, gets multiplied by a factor of 2. Okay, I hope everyone sees that. 2f of x is 2 times the function. Cool. And let's distribute in 2x squared minus 2x and plus 6. Box it up, and that's great. So you're going to see, obviously, I'm going to try to really show you the primary differences, input versus output, and really see that notation in action. Okay, guys, let's go get D. So letter D, f of x plus 1. And again, I guess I would ask you, are you changing x or are you changing f of x? And in this case, I hope you all agree that it looks like we're changing x. It was this, just an x inside the parentheses. Now that x has changed to x plus 1. So it is the x that changed, and so it is the input that is changing in this function. And so as a result, this basically tells us whatever the input is, I'm going to square it, I'm going to subtract it, and I'm going to add 3. And so knowing that piece, knowing the function rules, and then knowing that, okay, this is my input that I'm going to perform my function rules on, allows us to manipulate this mathematically. And so that would be it right there. Square the input, subtract the input, and add 3. And my input here is x plus 1. Cool. I would ask you actually to pause the video for a sec. This is something you're going to have to be able to kind of pull off on your own. Can you guys go ahead and do this piece right here? Can you expand that out? Well, let's see how you did. I'm going to do this in 2 steps just so you can see just in case. But when I FOILed that out, you got to be careful. Remember, this is not just x squared and 1 squared. It is x plus 1 times x plus 1, which is this. And then don't forget, distribute that minus in. So I got something along those lines right there, which means I have an x squared. It looks like I have a plus x. 1 minus 1 is 0. Add the 3, and I get that piece right there. So hopefully you're able to kind of get that as well, but that's what I get as an overall answer. Okay, now notice letter E, another plus 1. Does this represent to you an input change or an output change? Am I changing x or am I changing f of x? And in this case, I hope you realize that x hasn't changed. It was this. Here it is up there. Come on. And it is still this right here. But now it's f of x that I'm adding 1 to. I'm adding 1 to the overall function. I'm adding 1 to the output. Excellent. And so all this means for us is whatever the set of rules would be, in this case x squared minus x plus 3, all I'm going to do, guys, is add the 1. Mathematically, it's a pretty straightforward operation here, so x squared, how about minus x, and how about a plus 4? And there you go. All right. See those differences as we will kind of work with these ideas. Letter F and then letter G, everybody. So f of negative x right there, negative 1x, I guess. Looks to me like an input change. It was x, now it's a negative 1x. And so let's go ahead and put that piece in place if we can. And let's go ahead. How do I work with input changes? Well, very simply, if that is my input, just be careful on this one. I square the input, so I square negative 1x. I subtract the input, so I subtract negative 1x, and then I add 3. So understanding what your function tells you to do allows you to really manipulate any input. Now just be a little careful here. I will ask you to remove all parentheses when you put this in place. And notice, I'm very careful about this. This is what's being squared, this is what's being subtracted, and then I'm adding 3. So here's what I would say. This is actually a product raised to a power. Think of this as like a negative 1x, if you would. So I have negative 1 squared, and everybody, negative 1 is squared is actually just 1. So negative 1 squared is 1, and x squared is x squared. So as a matter of fact, when you remove the parentheses there, interestingly enough, it is just a 1x squared. And then minus negative 1x, so that just becomes a plus x and a plus 3. And that, everybody, is your overall answer. So just be careful on this piece. Over the years, I've seen students just have a little difficulty with that mathematics. That's what it turns out to be when you remove the parentheses. Okay, last one in this set right here. How about a negative f of x, or a negative 1 times f of x? And I'm hoping at this stage you can sort of see that that is an output change. I am changing the function. And so it looks like I'm changing the function by just putting a little opposite symbol out in front. Or really, when all said and done, just kind of multiplying it by negative 1. And that's what I'm doing, just multiplying the function by negative 1. So we're basically going ahead and distributing that negative 1 inside the parentheses there. And so this would be, watch this one, negative 1 times x squared. And that's how we would look at it right there. And then negative 1 times negative 1x, so that's a plus x. And negative 1 times 3, so it would be this right here. We will do some work on these last two, f and g, so just please see the differences and see how that plays out. This worked out this way in front. This one works out this way in front. Negative 1 times x squared. Okay, good. So I'm hoping it really solidifies that difference notationally between inputs and outputs here, and I believe we'll summarize this momentarily. Okay, so let's go ahead and summarize that, and then just do very quick little vocab work just down at the bottom there, just to get us going for the next lesson or two. So here we go, everyone. It says with an input change u, and I hope you noticed in each case, this is, I guess, how I would summarize it in just as basic terms as possible. So when we're dealing with an input change, we just replace all of the x values with the term inside the parentheses. Let me do that a little better for you. So with the term inside the parentheses. So I hope you kind of saw that. Anytime we sort of dealt with an input change, whatever that input was, it really replaced all the x's, and that's the bottom line. Okay? So input, just perform the function rules on that input, whatever it may be. Output changes are a little different, and here's just what I wrote. It looked like in each case we perform the operation on the entire function. So we're not replacing x's, we're not changing the x's, we're just changing the overall function by performing that operation. So that's what I pretty much wrote on my paper, and I'll do that on the board here. Perform the operation on the entire function. Perfect. And again, if you're comfortable with that previous example, then you intuitively did these pieces right here. I just wanted to summarize it for you on your notes worksheet. Excellent. We're going to kind of do a lot of work with these pieces right down below. So here's what I'm asking, see if I can fit this in here as well. But just really understanding what goes together, because you're going to really hear these phrases over and over again when dealing with functions. So it just says draw a vertical line down. Well, sorry about that. So why don't we go ahead and just match up these phrases here, what goes together in each pair. We'll get a set of 5 on the left, and then we'll get a set of 5 on the right, kind of matching it up. So let's start out, everyone. If we can go inputs, outputs. I guess you've heard me use those terms quite a bit during this lesson. So let's let them lead the way. Inputs on the top there on the left, and outputs on the top on the right. Now, as soon as you hear inputs, a variety of other things should come to mind. So it's basically just mental association with these other words on your paper, and same with outputs. So I guess the first order of business is to talk about inputs. As you've seen, they replace the x's. So why don't we go ahead and put x values over here, and when those x's go in, the y's come out essentially, or f of x. So we kind of did that with our diagram. So x represents the input, and the y represents the output. All right, very good. We're going to talk next lesson here about domains and ranges. So if you remember correctly, domain really represents all of the x values, and range would represent a set of all of the y values. So throw those together if you don't mind. And as I said, what you want to do is associate these things together and associate these things together. In terms of our algebraic modeling, of course, two variable quantities. If you remember from previous courses, basically the x would represent the independent variable, and then the y would represent the dependent variable. So you'll always hear it phrased, y depends on x. So y as the dependent, x as the independent. And then I guess the last one there, when we start getting into really analyzing the graphs, I will do some of that on tomorrow's lesson with domain and range, and then in future lessons dealing with transformations of functions. Really the last set I see is horizontal and vertical. And so just don't forget, when we're talking about x values on a graph, we're talking about the horizontal component to the graph. So let's go ahead and put that one piece in. So x represents the horizontal coordinates graphically, and then of course y would represent the vertical component, or the vertical coordinates of the graph. And so we're going to analyze graphs on the next lesson, really talking about domain and range. And I'll ask you, when you hear domain, think horizontally. When you see range, think vertically. And so I'm just kind of putting those together. Is it a necessity? Nah, probably not. But I think it's helpful. So these things all go together beautifully, and then these things all go together beautifully. All right, nice and straightforward there, everyone. Take a little time and just work with some of the manipulations of functions. As I said, you'll want to perfect it before we move forward and really utilize all this stuff. Thanks for listening, and please let me know if you have any questions.